Hi everyone, welcome to this lecture on general chemistry. We are still on Best Science Brain YouTube channel. If you are not subscribed to this channel, kindly move up to the subscription bell as the lecture is going on, the video is going on. Look for the subscription bell close to the channel's name, Best Science Brain. You see the subscription bell or icon. Tap on it once and get subscribed. Share our videos, make a comment. If there any question you want to ask a question on this YouTube and we'll answer it. So today we're going to general chemistry, a topic meant for freshers in the high institutions. We're going to talk about bond dissociation energy, which presents the symbol D. Bond dissociation energy, symbol D. So let's define this energy. Before we go ahead to explain this energy, just think of a molecule made up of different bonds. The energy required to break the bonds in this molecule is what is known by bond dissociation energy. So bond energy, otherwise known as bond dissociation energy, D, is defined as the energy supplied to a gaseous molecule to split it into component gaseous atoms or fragments. During bond cleavage, or cleavage means breakage of bond, energy is absorbed to break bonds. Hence, the process of bond dissociation is endothermic. So what are we saying? Bond dissociation energy, otherwise known as bond energy, is the energy required to split the bonds of a gaseous molecule into gaseous atoms. So, and this energy supplied is an endothermic. This process is an endothermic process because energy is absorbed to break bonds. So let's look at a correlation between bond energy and bond length. Bond energy and bond length. We know in chemistry we can have a single bond, double bond, and triple bond. Out of these three bonds, covalent bonds we have, triple bond is shorter compared to double bond, and then single bond has the longest bond length. So let's look at this. A relationship exists between bond order, bond length, and bond dissociation energy. Alkanes, alkenes, and alkynes have bond orders of 1, 2, 3 respectively. Alkanes with single bond, we say they have bond order of 1. Alkenes with double bond have bond order of 2. Alkynes have bond order of 3. Okay, let's continue. Carbon to carbon single bonds found in alkanes are the longest bond. As I say, single bonds are longer than double bond, and double bonds are longer than triple bonds, and will require the least bond dissociation energy. While carbon to carbon triple bonds found observed in alkynes are the shortest bonds and would require the highest bond energy. Let us consider the bond dissociation energies of ethane, 18, and ethane given below. So look at the first molecule. The first molecule there is ethane, H3C, CH3. If you look at it, is ethane, there is 2 carbon and 6 hydrogen. You see a single bond existing between the 2 carbon atoms in ethane. The energy to break that single bond into 2 methyl groups into CH3, and that CH3 is what's called bond dissociation energy for methane. You have it. You see methane split into 2 methyl groups in gaseous state, and the bond energy D is 347 kilojoule per mole for methane. So that is a single bond. You're going to see that single bond is among the 3 bonds, single, double, and triple. Single bond the weakest, and that means it's going to require the least bond energy. Let's go to the next example. 18. Look at 18, H2C, CH2. 18, that means, or otherwise known as 18 or ethylene. We have 2 molecules, 2 atoms of carbon and then 4 atoms of hydrogen. That is 18 in gaseous state. And the bond between the 2 carbon is double bond. That is 18 has bond order of 1. When we split 18 into 2 methylene groups, H2C and also CH2, that CH2 is called methylene group in gaseous form. We need 611 kilojoule per mole of energy. So you see that 18 requires a higher energy to split the double bond compared to arcane or ethane. So the higher the number of bonds, the higher the bond energy. We go to ethane. You see ethane, HC and CH. So have a triple bond between them. Ethane is C2H2. So if you want to split them into two CH groups, the energy required to split that triple bond is its own bond energy, and ethane requires 837 kilojoule per mole of energy to split the triple bond in ethane. So when you consider these hydrocarbons or the same number of carbon atoms, you see that the one that has bond order of 3, that is ethane or triple bond, requires the highest energy to split its bond compared to 18. 18 is higher than ethane, higher than 18, and 18 is higher than ethane. So the longer the bond, the longer the bond, the lower the energy required, and the higher the bond order, the shorter the bond, the higher the energy required, and the higher the bond order, also the higher the energy required to break the bonds. We'll now look at calculation of the bond energy of a molecule. So the bond dissociation energy D of a molecule can be obtained by adding the bond dissociation energies of all the bonds present in 1 mole of the substance. Let us consider hydrazine, whose structure is given below. Let's look at hydrazine. Hydrazine contains 1 nitrogen to nitrogen bond, as you can see, N to M bond, only one of it, and 4 nitrogen to hydrogen bond. Why is it 4? You can see on the nitrogen on the left hand side contains 2 of NH bond, nitrogen to hydrogen single bond, and then the one on the right hand side also contains 2 of nitrogen to hydrogen single bond. That are giving you 4. So we have there the bond energy of nitrogen to nitrogen bond is 159 kilojoule. That means you need 159 kilojoule to break nitrogen to nitrogen single bond, and the bond energy of nitrogen to hydrogen single bond, NH bond, is 389 kilojoule. To break each of the NH bond, we need 389 kilojoules of energy. So we'll now continue. Say, using the above data, estimate the bond dissociation energy of the molecule of hydrazine, that the molecule. So with this data, we'll also find the bond energy of hydrazine. So look at the solution. So there is only one N nitrogen to nitrogen single bond, as you can see, as I explained before, and there are 4 NH bond in hydrazine. 4. How do we count it? The left nitrogen has NH, and under NH that is 2. NH under NH on the right hand side, that is 2, giving you 4. So how do we get the bond energy of this molecule? So we add the bond energy of the energy required to break all the bonds in this molecule. So that gives you the bond energy of hydrazine. D means bond energy now. N to N single bond for nitrogen plus 4D N to H single bond. Why did I use 4? Because there are 4 nitrogen to hydrogen bond in that hydrazine. So we'll add the bond energies together. So bond energy of nitrogen to nitrogen is 159 kilojoules per mole. Bond energy of nitrogen to hydrogen is 389 kilojoule per mole, multiplied by 4, since there are 4 of such bonds. If you solve, we have 159 plus 1556. That gives us plus 1715 kilojoule per mole. So this is the total energy required to break all the bonds in hydrazine. That becomes the bond dissociation energy of hydrazine. So estimation of heat of reaction or enthalpy change using bond dissociation energies. So how do we calculate the heat of reaction when we're given the bond dissociation energies? So we say the formula given below can help us calculate the heat of reaction when the bond energies in the reactants. So the formula to calculate the bond dissociation energy of a molecule is given below. We read the formula given below can help us to calculate the heat of reaction. Sorry, the formula to find the heat of reaction, not the bond energy. So go back. The formula given below can help us to calculate the heat of reaction when the bond energies in the reactants and products are provided. So the heat of reaction, that delta H as standard state, begin as summation of M, that M stands for the stoichiometric number of moles, then D, that D is the bond energy of bonds broken in reactants, minus summation of N, that N stands for the stoichiometric number of moles as they appear in the balance equation, D, that the bond energy of bonds formed in the products. So this is the formula to calculate the heat of reaction. We'll take it again. Heat of reaction at standard state is summation of M, which is the number of moles in the balance equation, D, they are the bond energy of bonds broken in reactants, minus summation of N, which represents the number of moles, then D, bonds formed in products, where M is the stoichiometric mole of each reactant and small n stoichiometric mole of each product, and then capital D represent the bond energy. So let's see how this works out. Example 1 says estimate the enthalpy of formation of hydrazine N2H4 according to the equation or reaction given below. So we see that reaction showing nitrogen molecule. The bond between the two nitrogen atoms is triple bond plus 2 moles of hydrogen. The bond between the hydrogen atoms and the molecule is a single bond, giving us hydrazine. So we're going to see how we can find the heat of reaction based on this equation. So we are given the bond energy of nitrogen molecule, nitrogen to nitrogen triple bond, as 946 kilojoule per mole. That means we need 946 kilojoule of energy to break the triple bond between two nitrogen atoms. Then the bond energy of nitrogen to nitrogen single bond is 159 kilojoule. We need 159 kilojoule of energy to break the single bond between two nitrogen atoms. Then the bond energy of nitrogen to hydrogen is 389 kilojoule per mole. We need 389 kilojoule to break nitrogen to hydrogen single bond. Then we go ahead. The bond energy of hydrogen to hydrogen single bond is 436 kilojoules. That we need 436 kilojoules of energy to break hydrogen to hydrogen single bond. So go to the solution. The solution enthalpy of reaction which we are looking for is M, bond energy broken in reactants, minus N, bond energy or bonds formed in products. So we'll look at the reactants in the equation first. The reactants are nitrogen plus hydrogen. So we're going to add the bond energy of the reactants, total bond energy of reactants, so which is given by a summation of M, bond broken in reactants. So you can see the expression under, that is the bond energy of nitrogen to nitrogen plus 2 times the bond energy of hydrogen to hydrogen. So where is the 2 from? You can see there are 2 moles of hydrogen in hydrogen in the equation. So that one will have the 2 multiplying the bond energy. So we'll now substitute. The bond energy for nitrogen to nitrogen triple bond is 946. The bond energy for hydrogen to hydrogen single bond is 436, but multiplied by 2 because there are 2 moles of hydrogen in the reactant. So we now have 946 plus 4 times 436. That gives us 946 plus 872, giving us 1818 kilojoule per mole for the reactant side. We'll now go to the product. The product is hydrazine. So you can see hydrazine. So in hydrazine, there is 1 nitrogen to nitrogen single bond at the middle, and there are 2 nitrogen to hydrogen single bond on each of the hydrogen atoms. So that gives us a total number of 4 nitrogen to nitrogen single bond, 2 on the left nitrogen and 2 on the right nitrogen. We'll now move to the product. So we'll now calculate the total bond form energy required in the product, using the formula summation of N D bonds from the product. So that becomes D in the product. As I said, there is one nitrogen to nitrogen single bond, so D N to N plus 4 D N single bond to hydrogen. Why did I use 4 of NH bond? Because there are 4 of it. We count it, you can see the first one there where the cursor is, the second one, 2, the third one, 3, and the fourth one, 4. So there are 4 nitrogen to nitrogen single bonds. So that one will multiply D, and that is the bond energy of nitrogen to hydrogen single bond by 4. We now have 159 plus 4 times 389, and that will give us 159 plus 1556, giving us 1715 kilojoule per mole. Having calculated the bonds, total bond energy required for the reactants and that's required for the products, we now apply the formula enthalpy change, summation of bonds broken in reactants minus summation of bonds formed in product. We now subtract 1818 will go for the reactants minus 1715 will go for the product, and we got the final answer as plus 103 kilojoule per mole So we need 103 kilojoule per mole, or 103 kilojoule of energy is absorbed to break all the bonds in 103 kilojoules of energy is absorbed in the formation of, that means 103 kilojoules of energy was absorbed when 1 mole of hydrazine was formed from its constituent elements. That means of enthalpy change. 103 kilojoules of hydrazine was absorbed, because the reaction is endothermic. You can see the positive sign, plus 103 when 1 mole of hydrazine was formed from its constituent elements, which include nitrogen and hydrogen. So we'll go to example number 2. Example 2 says, estimate the enthalpy formation of tetrafluorohydrazine N2H4 with the reaction given below. You can see the reaction between nitrogen molecule and fluorine molecule. 1 mole of nitrogen molecule plus 2 moles of fluorine molecule, giving us tetrafluorohydrazine. So we are asked to find the heat of formation of tetrafluorohydrazine, and we're given the data. The data given to us will have the bond energy of nitrogen to nitrogen triple bond as 946 kilojoules. So we need 946 kilojoules of energy to break nitrogen to nitrogen triple bond. Then we have bond energy of nitrogen to nitrogen single bond. So we need 159 kilojoules of energy to break the single bond between 2 nitrogen atoms. We have nitrogen to fluorine single bond as 272 kilojoule per mole. We need 272 kilojoules of energy to break the single bond between nitrogen and fluorine, and then the bond energy of fluorine to fluorine single bond as 158 kilojoule per mole. Solution, we still go to our equation that says heat of reaction again by mole, that is M. So combination number of moles multiplied by the bond energy of the bonds broken in reactants minus N, which is the number of moles in the balance equation, multiplied by the bond energy of bonds formed in the products. We'll now go to the solution. The reactants. In the equation, these are the reactants. The reactants here will have a nitrogen molecule with 2 moles of fluorine molecule. So we have to calculate the bonds, total bond energy in the reactant, nitrogen and fluorine. So move ahead. We now have it under N number of moles multiplied by the bond energy broken in the reactants. So we go down there, we see D, that the D presentable energy of nitrogen to nitrogen triple bond, plus 2 times the bond energy of fluorine to fluorine single bond. Why do we multiply by 2? Because in the balance equation there are 2 moles of fluorine molecule. So that's why the 2 is in that 2 bracket D, F to F. So the bond energy for nitrogen to nitrogen triple bond was given to us in the data as 946 kilojoule, plus 2 times the bond energy for fluorine to fluorine single bond is 158. So we'll solve 946 plus 2 times 158 gives us 316. 946 plus 316 gives you 1262 kilojoule per mole. This is the total bond energy for the reactants. Then going to the products. The product is the tetrafluorohydrazine. You can see the structure there. So in that tetrafluorohydrazine, we move our cursor where the cursor is. We still have only one nitrogen to nitrogen single bond. Then by the right hand side we have NF bond there where the cursor is pointing, and that NF bond, two of the nitrogen fluorine single bond on the left hand side. On the right hand side we move the cursor, have another 2 NF bond and also another NF bond. So there are 4 nitrogen to fluorine bonds in tetrafluorohydrazine and only one nitrogen to nitrogen single bond in the compound. So the total bond energy in the product becomes D N to N single bond plus 4 N to F single bond. So the bond energy for nitrogen to nitrogen single bond given to us is 159 in the data, and the bond energy of nitrogen to fluorine single bond is 272 multiplied by 4, since there are 4 of such bonds. One would solve 159 plus 4 times 272 gives us 1088. Adding the 2, that will have 1247 kilojoule per mole. We'll now bring everything to the formula. The enthalpy of reaction is a bond energy, summation of bond energy or bonds booking the reactants minus summation of bond energy or bonds formed in products. So the reactant value is 162 minus the product 1247. We're getting plus 15 kilojoule per mole. So this is the heat of formation or the heat absorbed when 1 mole of hydrazine is formed from its constituent elements, which include nitrogen and fluorine. We'll now go to example 3 that says estimate the enthalpy formation of HCl gas using the equation below. So we have the equation for forming HCl. We have 1 mole of hydrogen molecule, a hydrogen molecule that is a hydrogen to hydrogen single bond, plus 1 mole of fluorine molecule, which contains also a single bond, giving us 2 moles of HCl, and also a single bond in HCl. So the bond energy for hydrogen to hydrogen atom single bond is 436 kilojoules. The bond energy for chlorine to chlorine single bond is 243 kilojoules. The bond energy for hydrogen to chlorine single bond is 431 kilojoule per mole. We apply similar process. The heat of reaction is total of bond energy or bonds broken in the reactants minus bond energy or bonds formed in products. For the reactants, look at the reactants, hydrogen molecule and chlorine molecule, and there's only 1 mole for each of the reactants. So we'll now add up the bond energy of hydrogen to chlorine. In the equation, summation of number of moles of bond energy of bonds broken in reactants. So hydrogen is given to us, that the equation D H to H plus D chlorine to chlorine single bond. The bond energy of hydrogen to hydrogen single bond is 436, while the bond energy of chlorine to chlorine single bond is 243. We'll add the 2 of them together, we'll have 679 kilojoule per mole for the reactant. Going to the product will have 2 moles of HCl. So we'll calculate the bond energy of bonds formed in the product. But in the product, we're having 2 moles of HCl. So we need to write 2D HCl. That D standing for the number of moles. That becomes 2 times 431 with the bond energy for hydrogen to chlorine single bond. So 431 times 2 gives us 862 kilojoule per mole. We'll now move with the formula, substitute. The enthalpy of reaction becomes bond energy of the reactants, that is 679 minus bond energy of the product, which is 862, that gives us minus 183 kilojoule. So, but we are asked to find the heat of formation. Heat of formation is the enthalpy change when 1 mole of a substance is formed from its constituent elements. You look at the balance equation. it was 2 moles of HCl that was produced in the balance equation. Let's go back to the balance equation. 2 moles of HCl. But we have to find the enter formation. Enter formation has to do with 1 mole, formation of 1 mole of HCl. But since we have 2 moles from the balance, from what we calculated, the heat of reaction calculated was for 2 moles of HCl, while the enthalpy formation should represent only 1 mole of HCl. So from what we obtain, we have to divide the heat of reaction by 2, 183 by 2, since the energy given out when 2 moles of HCl was formed is 183 kilojoule per mole. Then, since formation had to do with 12 mole, we now divide 183 by 2. We now have minus 91.5 kilojoule per mole. So this enthalpy of formation of HCl is isothermic because negative. So we have minus 91.5 kilojoule. So why do we divide by 2? Because the balance equation shows 2 moles of HCl. But the heat of formation is the enthalpy change when 1 mole of a substance is formed from the constant element. So divide by that value got by 2 to get the enthalpy of formation. Example 4. We have a reaction between 18 and oxygen, giving us CO2. So let's go back. 1 molecule of 18 reacts with 3 molecules of oxygen to give us 2 moles of carbon dioxide and 2 moles of water produced. So we are told that the reaction represented above shows the combustion of 18. Given that the heat of reaction or enthalpy of combustion is minus 1323 kilojoule per mole, use the data above to estimate the bond dissociation energy of carbon-to-carbon double bond. So in this reaction, when we have been given the heat of reaction given to us, but we have to find the bond energy of carbon-to-carbon double bond in 18. Carbon-to-carbon double bond in 18. That we're looking for. We're looking for the energy required to break this bond, where the cursor is pointing. Carbon-to-carbon double bond in 18. So what do? We follow the same process. We're given some data. The bond energy of oxygen-to-oxygen double bond is 498 kJ per mole. The bond energy of carbon-to-carbon single bond is 418 kJ per mole. The bond energy of carbon to oxygen double bond is 803 kJ per mole. The bond energy of oxygen to hydrogen single bond is 464 kJ per mole. Solution, we apply the equation. The heat of reaction is given by summation of bond energy broken in the reactants minus summation of bond energy formed in products. And we're given the heat of reaction as already minus 1323 kilojoules. So we're not looking for heat of reaction this time around. So let's go on. Reactants. The reactants are there, 18 and 3 moles of oxygen. So we'll now calculate the bonds formed in reactants. The bond formed in reactants is bond energy of carbon-to-carbon double bond plus 4 times bond energy of carbon to hydrogen single bond plus 3 times bond energy of oxygen to oxygen double bond. So let's find out. Carbon to carbon, look at the 18. Carbon to carbon double bond is only 1. There, you can see where the cursor is pointing. It's only 1 carbon-carbon double bond. Then carbon to hydrogen double bond. Look at this side. There's 1. The left where the cursor is pointing, coming down 2, going to the right hand side 3, and then down on the right hand we have 4. So there are 4. That's why I say 4 carbon to hydrogen single bond, 4 CH bond. Then oxygen bond, how many of them? Let's go to that. There are 3. Look at 3 O double bond oxygen. So there are 3 oxygen to oxygen double bond. Now I have that explanation that expression. There are 3 bracket D O, then bracket O. So, and we are looking for the bond energy of carbon to carbon double bond. So it's unknown. Then we'll substitute with the value of carbon to hydrogen single bond, which is 414 multiplied by 4, plus the oxygen to oxygen double bond. The bond energy is 498 multiplied by 3. We'll solve out. We'll have D C to C double bond plus 4 times 414 is 1656 plus 3 times 498 is 1494. So adding 1656 to 1494 will give us 3150. So we have the unknown Bond energy of carbon to carbon double bond unknown. So we're looking for that. Going to the products. In the products, we have the bonds there. We have 2 molecules of carbon 4 plus 2 molecules of water. So we want to find the total bond energy of the products. So for the products, they gave us the bond energy of, in the data, the bond energy of carbon to oxygen double bond. Why do we say 2 times 2? Why do we have 2 times 2? So they gave us carbon to oxygen double bond. The carbon to oxygen double bond are called 2 times on the left hand side of carbon and on the right hand side of carbon. That means 2 of CO bond multiplied by the 2 in front. That will give you 4. So that's the reason why we have 2 times 2 of bond energy DCO. That CO is 2 times, that is from left hand side and right hand side of CO2. If you go to water, the OH bond in water are called 2 times also. OH on the right hand side where the cursor is pointing, and also OH on the left hand side of oxygen where the cursor is pointing. So you see be 2 times 2 OH bond in water. So you can see it there. 2 times 2 OH bond energy of 2 times 2 DOH for water. So we now have 2 times 2 is 4 multiplied by the bond energy of carbon to oxygen double bond, which is 803 given to you. Then 2 times 2 for water is 4 multiplied by bond energy of oxygen to hydrogen single bond, which is 464. So 4 times 803 gives us 3212 plus 4 times 464 gives us 1856. If I add 3212 to 1856, I will get 5068 kilojoule per mole. So we'll now substitute. The heat of reaction have been given to us, that the heat of combustion given to us already in the equation as minus 1323 equal to the bond broken in the reactants, or total bond energy in the reactant becomes D, which is unknown, bond energy of carbon to carbon double, which we are looking for, plus 3150. Then minus the bond energy for the product, which is 5068, which we obtained a few minutes ago, 5068. So we'll now make that D. We'll now add 3150. 3150 minus 5068 gives us minus 1918. Bringing it down. We'll collect items on making D, bond energy of carbon to carbon double bond, the subject. D, C to C double bond is equal to minus 1323 plus 1918. That gives us plus 595 kilojoule per mole. So this is the energy required to break carbon to carbon double bond in alkenes. Example 5 says methanoic acid is formed according to the equation below. Graphite, that is carbon, plus oxygen to oxygen double bond plus hydrogen to hydrogen single bond, giving us methanoic acid. So we examine it. Oxygen contains a double bond, hydrogen molecule contains a single bond, and in methanoic acid there is 1 carbon to hydrogen single bond, 1 carbon to oxygen single bond, 1 oxygen to hydrogen single bond, and 1 carbon to oxygen double bond. So we are told if the enthalpy of formation of methanoic acid is minus 378.6 kilojoule per mole, estimate the bond energy of carbon to oxygen double bond in methanoic acid using the data below. So we are giving the oxygen to oxygen double bond, the bond energy as 498, the carbon hydrogen to hydrogen single bond, but the bond energy is 436, carbon to oxygen single bond, the bond energy as 351, oxygen to hydrogen single bond, the bond energy at 464, carbon to carbon single bond, the bond energy at 719 kilojoule per mole. Then carbon to hydrogen single bond, the bond energy at 414 kilojoule per mole. So let's go to the solution. Solution, the formula we need is there. The enthalpy of reaction is total bond energy of reactants, bonds broken in reactant minus total energy of bond formed in products. The reactants are graphite plus oxygen plus hydrogen. So we now add the bond energy of these substances together. The bond energy of graphite, carbon to carbon double bond for graphite is 717 given to us. The bond energy for oxygen to oxygen double bond is 498. The bond energy for hydrogen to hydrogen single bond is 436. We add everything together. That gives us 1651 kilojoule per mole. We now go to the product. The product is only methanoic acid. We now sum the bond energy of bonds formed in the products. We have a bond energy of carbon to hydrogen single bond. You have one of it in methanoic acid. The bond energy of carbon to oxygen double bond, which is, you can see one of it, carbon linked to oxygen underneath with a double bond. The bond energy of carbon to oxygen single bond, carbon to oxygen by the right hand side, and the bond energy of oxygen to hydrogen single bond at the extreme. So you see that. So add everything. The bond energy for carbon to hydrogen single bond is 414. The bond energy of carbon to oxygen double bond is what we're looking for, that DCO. The bond energy of carbon to oxygen single bond is 351, and that of oxygen to hydrogen double single bond is 464. So we now add 414 to 351 to 464, and we're going to get 1229 plus bond energy of carbon to oxygen double bond, which we are looking for. Okay, we're given the enthalpy of formation in the reaction as minus 379.78.6, and that's the heat of reaction. We'll now replace the heat of reaction in that equation with minus 378.6 with the enthalpy formation equal to the total energy of bonds broken. Have a calculated area on as 1651 minus then the bond total energy for bond formed in the product, which you did just a few minutes ago, 1229 plus DC double bond oxygen. So minus that 1229 plus DC, that is substituting in the formula we have above. We'll have this plus DC, then double bond oxygen. So having done that, we'll now go ahead and then solve. 1651 minus 1229 gives us 422, which is under. So we'll bring down the values. Minus 368.6 equal to 422 plus D carbon to oxygen double bond. Then we'll solve again. We'll now have D carbon to oxygen double bond gives us minus 368.6 minus 422, and that will give us minus 800.6 kilojoule per mole. And the bond dissociation energy is an endothermic process. That why the value was changed to plus 800.6 kilojoule per mole, because it's an endothermic bond dissociation is an endothermic reaction. So that brings the lecture to an end. Next, we're looking at drawing of Lewis structures of molecules and ions. We're also looking at resonance structures and bond order. So if you are not subscribed to this channel, please kindly move up the channel's name, and close to the channel's name you see the subscription bell or icon. Tap on it once and get subscribed. We can share our videos to your friends. Share our videos to your friends, your classmates. Let them know of this channel, so it will help. They will learn chemistry with us and general physics with us. Even the practical lessons we display on this channel from time to time. Thank you for listening and have a wonderful day. Thank you.